Those of you that were not here during number sense or math, I'm Larry White, the math contest director and the number sense contest director. This is my 5th year doing this. I taught public schools, high school mathematics and computers for 27 years in small schools most of the time. Then I taught 7 years at Angelo State University teaching math, teaching teachers how to teach math. And then I retired again, and now I'm in charge of the Mathematics for English Language Learners Initiative for Angelo State University. And I handle about a $250,000 a year grant, and I love to spend all that money on teachers. In my free time, I do UIL. I have a private computer business, and all the rest of the time that I have free, I just goof off, which is a lot of goof off. But that's basically what I am. The most important part of this about this whole thing is my email. If you want to email me, coaches, about any questions or answers, I can legally give you shortcuts and solutions without any problem, as long as it's not something that gives you an advantage over someone else on a new problem, for example. And then all I can do is tell you, I'm sorry, I'm not able to respond to you concerning that, but I may lead you somewhere where you can get a response. So be sure to use that. If students have a question, please have them do it through you. I get about 200 emails a day, and I just don't have time for many more. And then the other important thing is that phone number. That's my home phone. You can contact me there during district and regional in case you think there's an error on the test. Because technically you're not allowed to change the key or the problem without contacting UIL and getting approval. It's not that we don't make mistakes. It's that if you find a mistake, you need to get my approval, and once I approve the error, I can contact all the rest of the districts and regionals so that they're on the same playing field. So be sure to have that number. If something happens and you can't reach me there, if you reach my answer machine, it'll be something like, welcome to the White House. We're not available at this time. All the interns are out to lunch. It's not really the White House, it's the White House. But anyway, it's a lot of fun. But call UIL. They can reach me by 2 cell phone numbers. They won't give them to you, but they can reach me, and I will call you immediately. So I'm available 24 hours a day during all of both district time and regional time to answer any questions and make sure that everybody's on the same playing field. So that number and UIL number is important. If you're looking for any instant notices about the test, any corrections or any comments or whatever, look at the UIL webpage under academics. On the bottom right, you'll see a section down there where it has math and number sense. And if I want you to know something real quick, I'm going to post it as soon as I want you to know it, so you don't have to wait a year and find out that there was something wrong and you didn't know that. So keep an eye on that page. And I'm always writing a few little interesting articles and things and throwing them down there as well. So keep an eye on that page. It's a real nice way to keep up to date with what's going on. Okay, that's enough of that stuff. We're ready. Now, where did I do the... I don't know. We're going to talk about some special areas. And I always find this rather interesting. This has the shape of a rectangle, and no one has any trouble finding the area of a rectangle, right? Length times width, whatever. Base times height, it's all pretty easy. The only problem is, out there in the world, there aren't many rectangles. Most things out there in the world I hate these new Ziploc bags. You never know when they're open. Most things in the world look like that. They have odd shapes. They're nice, not nice, pretty little rectangles and circles and squares and trapezoids. They look like that. We have to be able to find areas of things like this, because that's what life's all about. So we're going to talk about some special area techniques. Some of them of which some of you have seen, but I know of 3 that I don't think you have. So that'll be interesting. Anyway, to begin with, suppose I take this envelope and I draw 2 diagonals and I cut the top part off. For example, I did this one, and I cut the top part off. So now it's no longer a rectangle, now it's a pentagon. Yes, pentagon. But it's interesting to note that if I do that, and then I fold it, if I can get it to behave, get in there. There you go. Little humid in here or something. Anyway, if I fold it, that 2-dimensional figure that was once a rectangle has now become a 3-dimensional tetrahedron. Yeah. The pyramid called the tetrahedron. So it's rather fascinating. You see, if you take an envelope and cross it with a tetrahedron, you get a tetralope. Now there's something interesting about this. If I took the area of the front of this rectangle, you know what the relationship between the area of this and the surface area of this 3-dimensional figure is? Do you know? Well, let's find out. There's the whole envelope. Notice the green part is half of the front. Green part's half of the front. If the surface area is all of the green, then the area of the surface area of this tetrahedron and the area of this envelope is the same. That's rather unbelievable, isn't it? I thought so. It's interesting. See, you put that away so I don't lose it. Yeah. Here's a fun thing for you. I don't know about you, but I grew up in a rather large family. I had 6 brothers and a sister. I try not to talk about my sister because she was spoiled. She got everything. 6 boys. 7 boys, they just didn't get anything. She got everything. But anyway, when it came down to dividing up food, we didn't have a real neat way to do that. First off, we didn't have a lot of food, but we didn't have a real neat way to do that. So my parents were real smart. My mother and sister got their share, and then they opened the door for the rest of us to come in, and we jumped off. But anyways, you ever taken a pizza and cut it up, like, or the pizza guys cut up, you know, and everybody takes a piece of pizza, and somebody says, you got a bigger piece than me, and all that kind of neat stuff. How in the world do you get a pizza that's exactly, the slices are the same? Interesting. Are those slices the same? Ironically, if you took 2 slices and gave your 2 friends 2 slices, you could all have an equal amount of pizza. Which 2 slices are equal? If I took these 2 right here, what other 2 can I take to be the same? These 2? How about these 2? How about these 2? Ironically, yes. There are 4 pairs of equal slices. These 2 are the same as these 2, are the same as these 2, same as those 2. They don't look it, but they are. If I took the purple and the green piece two pieces could you take to be the same? The white and the brown. Blue and yellow. Whatever that is and whatever that is. I don't know what the pink and brown, light tan. Yes, they're all the same. But notice, it's cut differently. This is cut from over here. This is cut from there. All right. I'm going to take pieces 4 and 8. Which ones do you want? 3 and 5, 1 and 6, 2 and 7. And look, they're cut differently. There's that telephone. I wonder if it's this one. Hello? You think so? Okay. He's going to offer you $32,000. Deal or no deal? Good pass, I know. That's so bad. Anyway, it's interesting to note that it does not matter where I cut the pizza at. As long as I pick a point somewhere in this circle and I draw 45-degree angles from that point, I will always end up with pairs of equality. If it's in the center, it's natural, isn't it? It's right through the center, but it doesn't matter where that locus is, where that point is. You can move that point way down here, move it over here, move it up here, as long as each one of those things are drawn perpendicular, and then you do the perpendicular of those, you can have 45-degree angles, and those pairs will always be equal. That's rather fascinating. Didn't know that about pizzas, did you? You do now. All right? What kind of triangle? Can't slide it by these guys either. Smart one, boy. How do you know? Actually, you can know lots of ways. The little symbol, you could know the numbers and see if they meet the Pythagorean relationship, or I could tell you, and I did, so you're right. How do you find the area of that right triangle? Base times height, chopped in half. Everybody knows that, no big deal. What kind of triangle? How do you know that? I told you so. That's right there. And in an acute triangle, you can take the base times the height, chop it in half, and get the area. Do you understand that there is another base, and another height, and another base, and another height? They will all result in the same information, the same deal. But it doesn't have to be this one and this one. It can be any one of the three. All right? What kind of triangle? Very good. You got it short. Once again, base times height chopped in half. But notice where all the bases and heights are. Here's the normal base. And it doesn't look like a base. It's not sitting on its base. But base, and there's a height. And here's another base. And its height's way over here. Here's another base. And its height's way down here. So you have to be careful. But either way, base times height chopped in half will work if you have enough information. All right. What kind of triangle? I didn't tell you, did you? Oh, blew your minds on that one, didn't you? What kind of triangle? Equilateral. How do we know? All the sides are equal? All the angles are equal. Equilateral. How do you find the area of an equilateral triangle? Base times height chopped in half. But suppose you don't know base times, the base and height. Suppose you know the sides. Those of us especially in number sense know this. It's the square root of 3 over 4 times x squared. But suppose you don't know x, suppose you know the height. Square root of 3 over 3 times the height squared. Now, the biggest problem becomes students say, how do I keep those apart? How do I know if it's h squared or side squared? Well, it's really pretty easy to think because you see 3 comes before 4 in the numerical scheme, and h comes before s or x in the alphabetical scheme. So, pretty easy to remember. After. Huh? What kind of triangle? Isosceles. By the way, just for the fun of it, do you see any more isosceles triangles up there? How many? 3 of them, aren't there? Why is an equilateral triangle isosceles? At least 2 sides are congruent to be isosceles. So this is isosceles and these are isosceles. But that does not reverse backwards and say if it's equilateral, it's isosceles. If it's isosceles, it's equilateral. So you have to be careful, make sure you read it. By the way, how do you find the area of an isosceles triangle? There actually is a formula. It's ugly. There's a formula. But I'm going to show it to you because it's ugly. Base times height probably is the best way to attack it. Divided by 2, of course. Sometimes we don't know everything that we just went over. Sometimes we have a triangle like this, and we have to find the area. How do we find the area using this information? A times B times the sine of C chopped in half. Really nice to know. X times Y times the sine of W chopped in half. Nice to know. Sometimes we get caught with this. Where we know 3 sides. How do we find the area? Heron. Mr. Heron. Heron's formula says we find the semi-perimeter, which in this case is pardon? 9. And then we take that semi-perimeter times the difference in each of the sides, and then take the square root. So we have 9 times 4 times 3 times 2, and we take the square root. Right? Whatever that may be. What is that? 9 times 36 times 3, 108 times 2, 216? Is that correct? No, it's not right.
636.
9 times 4 is 36 times 3 is 108 times 2 is 216. So what's the square root of 216? Ah, you got to have a machine for that one, huh? What's the square root of 225? What's the square root of 196? Which one's closer to 216? 15, right? So it ought to be somewhere around 14.7. You don't need a calculator. Right there. Right there. This is how some people beat some people on the math test. They don't need that machine to find the square root of 216. They can look at the answers and see those things and do a little interpolation and go, high-low game. Pretty nice. Good? find the area of these two triangles. Don't know the base. Don't know the height. Don't know the angles. Don't know much, do we? Well, let's play with the little one first. How many boundary points do you see on the little one? 3. How many interior points do you see? 1. Well, let's see. If we take the boundary points and chop them in half, we get 1.5. We take the interior points and take away 1, we end up with, and if we add those together, we get the area of that triangle is 1.5. That comes about from a mathematician named Pick. I can line this up right. Pick's theorem. You take the boundary points and chop them in half. You take the interior points, you take 1 away, add them up, you get the area of the triangle. It's pretty neat, isn't it? So you see down here, boundary points, we have 1, 2, 3, 4, 5, 6. Chop in half, we get 3. And then we got 1, 2, 3, 4, 5, 6, 7. Take 1 away, is 6. 6 and 3 is 9 square units. Oh, look, up the little blue one up at the top. Boundary points. 9 interior points. 2. So what's the area? 5.5? 9 chopped in half is 4.5, and 1 of those interior points, 5.5. If you don't believe that, if I take this rectangle, go all the way across, I'd have 8. But if I chop it here, I get 1, 2 taken out, and I get 8. Oh, there's 10 boundary points. Yeah, it should be 5. Oh, so it should be 6. Yeah. And there's, I caught myself with that there. So you see, you can count all these red boundary points and count all these dots, apply picks, and find the area of that funny-looking triangle. Which, by the way, in case you're interested, there are 26 boundary points and 54 interior points, which gives us an area of 66 square units. Okay? With that in mind, guess how you can find the area of that leaf? You can trace that leaf on there, find the boundary points, the interior points, apply picks, and you can find the area of a funny-looking object. Estimate, of course, but then isn't everything an estimate when it comes to this kind of stuff? But that's pretty neat. Now you know how to find the area. All those weird things out there. I thought that was pretty fascinating. I have no idea what the area is. Somebody asked me once, why would we care? Well, it appears, and I'm not a science person, but it appears that chlorophyll is created or grown or whatever through leaves based on the amount of surface area. I don't know all there is to know about this, but it has to do with science, and they have to know the area of these things to know how much is being produced. So it's valuable, I guess. Just don't eat the wrong leaves. Huh? Okay. Have you learned anything new yet? Good. I got more for you. I'm going to teach you some real new stuff. Now, due to the fact that I made extra thick lines, we really don't know which ones are boundary points and which ones are not, and all that kind of hoopla. I fixed it in such a way that it's almost impossible to tell what the height and the sides are without using a bunch of Pythagorean relationships. I sort of fixed it intentionally this way because there is another way in which we can find the area of all polygons, not just this one. I just happened to pick this one because we're talking triangles. Do you know what the coordinates of that those of A, B, and C are? I believe that ought to take care of it. Is that correct? Agreed? That I didn't make a mistake? Well, it's interesting to note that I can take any one of those points, and I don't care which one, I just chose 3, 4 just for the fun of it, and I can list them in pairs, like in a table of, an XY table, 3, 4, 14, 3, 9, 8, and I have to be careful to make sure that if I start at 3, 4, I end with 3, 4. I have to go and come back. All right? So I list those in a nice table format, and then I multiply. 3 times 3 is 9, 14 times 8 is 112, 9 times 4 is 36. And then I go the other way. I started to say I cross multiply, but you know cross multiplication is not a good math word because it really doesn't exist, so I didn't say that. And I multiply 14 times 4, 3 times 9, 8 times 3, and I add those. If you add those two sums and divide them by 2, you find the area of that figure to be 25 square units. That comes about from a man by the name of René Descartes. Now I say that René Descartes because that's the only way I can spell it. His name is René Descartes. But I can't spell Descartes. So I say Descartes. And ironically enough, it does not have to be just a triangle. And they don't have to be just in quadrant 1. They can be in any of the quadrants. It can be any size, any figure that doesn't cross, any simple closed figure, as long as they're not complex. They don't cross. That technique works every time, regardless of what you have. Rather a neat one to play with, especially if you happen to be doing something geometrically and you don't have any measurement stuff. You can take that geometric thing and put it on a grid and do that, and then you can scale it to a large model if you choose. Drafting is very much into this thing. It's really a rather fascinating technique. The key is pick any point, go counterclockwise. You can go clockwise, but you have to be careful because you have to do some reversal of numbers. So it's easier to go counterclockwise and make sure if you start with 3, 4, you end with 3, 4. If you don't, it won't come out right. Rather neat, isn't that? Mr. Descartes. René Descartes. He's pretty phenomenal. Stone man again. That pizza man's going to get here sooner or later. No doubt in my mind. Now it starts to get interesting. How did I do this? Oh, I got an extra sheet of paper. Now it starts to get interesting. What kind of polygons do we have here? How do you know that? So, you guys are bright. How else would we know that? Yeah, the appropriate marking, mathematical marking is there. It tells us there. So our first figure is at equilateral triangle, then a square, then a pentagon, then a hexagon. And I just chose those just for the fun of it. It doesn't matter as long as they're regular. We know how to find the triangle, the area here, correct? We can find it lots of ways. AB over 2. We know the sides, herons, all sorts of different ways. We can find the area of a square pretty easy. How about a pentagon? We could draw a line across here and find the area of a triangle and the area of a trapezoid. That would work. Or we could draw it straight down and have 2 trapezoids. That might work. How about the area of that hexagon? We can break them up into equilateral triangles. 6 equilateral triangles. We can do 2 trapezoids in a rectangle. And you know, that's what becomes the problem. We can do lots of things depending on the information we have. I have a math book at the house. I've had it for many, many, many years. It's got 600 pages in it. And it's got nothing in it but math formulas. Not problems, not solutions, not explanations, formulas. I don't know about you. I'm good, but I ain't that good. I can't remember all those formulas. People call me up on the phone and say, can you find the area, the volume of this particular object? And they'll describe it. And I said, sure, just give me a few minutes. And of course, they think I figured. Really, I'm flipping over that formula book because I don't remember all that stuff, nor do I want to remember all that stuff. We get caught in the same thing here. We teach all these different formulas. And that's okay. There's nothing wrong with that. And it's nice to know basic formulas. But there are actually ways to find it given information. There's a way to find every one of those given side lengths of regular polygons, given side lengths. There's a way to find the area of those items one way. I'm going to show you that in a minute. Here's another one that pops up where the circle is inscribed in the polygon, and all of a sudden we have a segment that forms a perpendicular to the sides, and we call that an apopum. You know what an apopum is? In West Texas, it's a little furry little animal with a long tail, and little kids things are on its back. We call them apopums, and we shoot them a lot. The apopum is the perpendicular. We sometimes refer to it as in radius. And then we have where the circles circumscribed around. The object is inscribed inside. And then the center to the vertex is called a radius. Okay, you got all that? Good. I just picked the pentagon just for the fun. Doesn't make any difference. As long as you have a regular figure, polygon, and you know the length of one side, you can square that side, multiply it by how many sides there are, and divide it by 4 times the tangent of pi over n. And you'll know the area. So in this case, I can take side squared, which is 3/4, that'll be 9/16 times 5, divided by 4 times the tangent of 180 divided by 5 is 36. And you'll find the area. And it does not matter what size regular polygon it is, as long as it's a regular polygon. It can be a triangle, square, a pentagon, a hexagon, a heptagon, a nonagon, a dodecagon. It doesn't make any difference as long as you have it. You can do that off of the side. How many people knew that? Oh, good. A few people, that's good. How many of your kids knew that? Uh-huh. How many of your kids are going to know that? Uh-huh. Suppose I've given the apopum. Then I can square the apothem and multiply it by the number of sides, and multiply it times the tangent of pi divided by the number of sides. So in this case, it's 1/2 squared times 5 times the tangent of 36. Now you do understand that if you have a calculator and you have this knowledge, this problem's very fast. Pardon? Yes, I'm sorry. Everything we're talking about here is regular. Otherwise it will not work. It has to be regular. But you see, if you know that, it's very simple to throw that into a calculator. That's where a calculator is appropriately used. Now, of course, if that was 30 degrees instead of 36, it would make a difference, but we're not going to get that. And of course, if you happen to know the actual radius, you can square the radius times the number of sides times the sine of 2 pi over n and chop it in half. None of this, by the way, is made up. It's all been proven. It's all fact. It's all there. Every year I like to try to find a couple of interesting things that sometimes we've lost in our curriculum because our curriculum got overrun and we don't have time to deal. And so I like to go play and find things. And I was messing around with Higgs theorem one day and Descartes, and something just popped into my mind. I want to see what would happen if I could find some standard equations. So I went playing, and I decided I was going to pull these up and throw them out there and introduce you to them. And then, of course, you know what's going to happen from here. You're going to see some of this stuff on the test, because you've learned something new, or if you didn't already know it, you need to share it with somebody along the line. Questions? Nobody? Questions? Blew your mind with lots of knowledge, your brain goes. Mine gets that way after a while. Anybody? Anything for the math test you want to ask me while we're here? Everybody ready to go home and have lunch? I knew I'd get a response out of you. It's just a matter of time. Yeah, by the way, did anybody come back looking for a phone? Somebody's going to be one disappointed person. All right, well then, in that case, you need to be sure that you've signed the roster. Leave your blue sheets on the floor, on the sides. And I hope you have a great year, and I see you at the big show in the big city in May.